Hi folks, I'm in here for Projects Done. Today I'm going to talk about a great project of mine I did a long time ago. I did it back in 2009 when I was 18. And we're talking a lot about electronic circuitry, especially electronic circuitry digital level and the hardware level, not the software level. So I'm talking about those circuits in which you have to design, and then connect all the wires together to make the circuit work in a certain way. Not the ones you can just type into your computer and compile the program and load it to your microcontroller. No microcontroller used. Believe it or not, there's no microcontroller controlling the whole project. It's all built with digital circuitry in the hardware level. So I guess what I'm trying to say is that without any program. So you might wonder what this is, and for now I could just say that this is a power supply capable of supplying about 1.2 to 24 V, 24 volts, AC or DC, and up to 5 amperes. Up to 3.2 amperes actually, but these old power supplies, they can give you a little bit more amperage with no problem. And it has the overload protection, it has lots of other features which you can find out in the rest of the video. Thank you. Oh well, doesn't she look pretty? A benchtop power supply. You see most of these power supplies, they can give you voltages between 0 to 30 volts. This is a little different than that. It can give you a voltage between 0 to 24 volts. But it has plenty of other options that are very useful for a benchtop power supply that I wonder why they're missing in all of those power supplies. Alright, so I'm going to make it short for you. Before I turn it on, I would like you to actually see all around it. Before starting though, I'm going to talk about the display. So it has the lower display and the upper display. The lower display has the transformers. It includes all the transformers and everything inside. It's just made for power. And it's going to give you all the readouts, say the output voltage, the output current, and the input voltage. Of course it's off right now, so you can't really see anything until it's on, and that's the beauty of it. And you see the upper display. The upper display actually gives you all the controls you need. So there's no changes you can make to the lower display. It's just a readout display. However, the upper display has all the controls. It has the polarity, it has the AC or DC, it has the open or closed circuit option, it has the fixed voltage option, which I'm going to talk about later because it's all off right now and you can't really see anything. So moving on, we're going to talk about how this device is being controlled, right? It has all these options, but how can you really control this device? Well, it has 4 buttons, and 4 buttons only. You can find these 4 buttons on the body of the device. You can find it on the what I would call the desktop remote control, which is actually wired. It's going to be wired to the device, but you can put it anywhere on your desk as you wish. Anywhere that you feel comfortable, you can just put it there and use it right there. It's actually, if I wanted to buy a power supply on the internet, or if I wanted to buy a power supply in the market, that's what I would be looking for. Really, this is really missing from all the power supplies. I don't really need a remote control. I just need something handy, Alright, so moving on. It has the same, I forgot to mention, it has the same 4 buttons here, right, left, down, and up. And you can find them here, right, left, down, and up, but there's a difference. These are buttons, but these ones are just finger touch buttons. The same as the turn on button. It's also finger touch. Yep, it's all done by logical ICs, the 4000 series, CD4000, and they just do great. If you get to stabilize the voltages and everything, they're not going to make any mistakes at all, and that's the beauty of logic ICs, which microcontrollers are missing. I know they have a watchdog timer and everything else, but it doesn't really serve the purpose. I think the logic ICs, the best thing about them is that they never make mistakes, or they hardly ever make mistakes. Anyway, so let's go to the back. In the back you see that there's a plug, of course. You may wonder why it's so short. It's because actually it has an extender, but this extender is lost. I lost it during coming to Malaysia. It's just, I don't know. The extender and also the remote control, I lost them both. I feel kind of sad about that. And the terminals that are connected to this benchtop remote control are right here. They're connected from here. And this benchtop remote control comes with its own plugs, of course. These are the plugs. You can connect the plugs right here. You can plug them in. Yes, this is a keyboard plug, and this is a keyboard wire. And if I haven't told you already, I actually made it with all the things that I had at home. So I bought only a few things for it. This is actually a keyboard wire. I just cut it at the keyboard and connected it to this benchtop thingy. And right here we have the female version of the plug. And you get the plugs, everything, nothing special about that. But if I want to show you a little bit closely, yeah, you could see the desktop volume socket, and I even had a model for this. It's made in Earth, made in Iran actually. And it has a voltage selector because back in Iran we had 220 volts, and outside in here in Malaysia we have 230. And then you have the beep option in here. Yes, I added a little annoying beep option, so if you turn this on, whenever you press a button, it's going to make a beeping sound. It's going to make a noise. And you have two fans in here, right? I have two fans in here that are going to suck the air from the inside out. And I could make it the other way. I could make it in a way that is going to, push all the air inside. But I wanted to suck the air so then I can make any holes anywhere I like inside the device, and whatever is behind that hole is going to be cooled down by the air that is being sucked in. So after a bit of while that is going to be turned on, you see that the hot air comes out. It might be surprising for you, why would the logic circuit give you hot air? Well, because these old logic circuits are current hugs. They actually consume a lot of current to do simple tasks. But the advantage of that is that they never make any mistakes, if you manage to make them right. In this power supply though, they make sometimes mistakes because at the time I didn't know that I had to use a regulator. There's no regulator used inside this. Believe it or not, there is no regulator, and that's why sometimes it makes some mistakes. So please forgive this device. So that's a tour. I think I haven't shown you the top of the device. This is the top. I made all the holes myself with a drill. This is the antenna. This is used for the RF remote control that has the same 4 buttons as you see right here. Everything is just 4 buttons. That's what I love about this thing. So that's about it.
Alright, at this point actually the power supply is off and the switch has not been turned on. The switch is off. So I'm going to go ahead and turn the switch. Once I do that, you see that it has this kind of selector LED that goes around and goes back and forth, and it's just some sort of a visual effect I think I added to this just to make it look nicer. So if I want to turn this on, I would have to touch this button here. It turns on. And by default, there are some settings into this, and by default this is supposed to blink. By default it's going to show some number like 88 or 89% something. This means percent. This is up arrow, this is down arrow, this is forward arrow, this is 0, of course, 24. This is the number of voltages this power supply could have. Let me just tell you how it works. So I told you about the buttons here, that it has 4 buttons. And these buttons, this is the forward, right? So if I press it, the LED is going to go forward, right? And this is the backwards. So if I press it, the LED is going to go backwards, but it's going to stop there. It's not going to go anymore. So the forward is like an endless loop, but the backwards is not. And this is the output voltage, but it's only going to show you the DC output voltage, not the AC one. This is the amperage output, CIO, VO, and this is the VI, which is the input voltage. We have 245 volts AC coming inside of this power supply, which is a little bit too much for this. This was designed for 220 to 230 volts. This is a little bit too much, so I can't really turn it on for too long. I'm just going to demonstrate the options here. So I can go forward, right, and then I can press this, and it will stop. So once it's blinking, actually, it's on the regulator mode, which means you can have a voltage between 1.2 volts up to 24 volts, and depending on the percentage you have in here. Is it 10% of 24 volts? Is it 20% of 24 volts? Is it 15%? Is it, I don't know, 35% or whatnot? Is it 0%? It could be just nothing. So you can also change the voltage you see in here. 24 volts, 18, 13, 12, 9, 7.5, 6 volts, 4.5 volts, 3 volts, and 1.5. If I press it again, it goes back to 24. I wish I had actually made it somewhat a stopping there so it doesn't go back to 24. It's like not really safe, but well, I didn't think about it at that time. And if I press the forward, and then press up, this is going to make it a closed circuit. Press it again, it's going to make it a open circuit. I can choose AC or DC, whatever voltage I want. I can choose the polarity. So AC and DC only applies to the voltage, the set voltages here, 1.5, 3 volts, 4.5, etc., etc. You can have it both in AC or DC, but if you set it on the regulator, you're only going to have the DC voltage. The AC power supplies are something different. The AC power supplies that can give you a variable voltage are different. They're transformers basically that have a knob on them, and then you can turn that transformer's connection on the coil, and then you can get a different voltage of AC. So that's a different story. Alright, so I just connected the lamp. So it's on 3 volts, but as you see, the circuit is open circuit. So I'm going to go ahead and make it a closed circuit. You see we have almost 0.5 amps going on. The voltage has been reduced, but the lamp is barely on. You can see, just slightly on. It's nothing really, it's just getting warm. The lamp is just getting warm. So I'm going to go ahead and give it a different voltage. Now this is going to go crazy. It's going to be 24 volts. Check this out. Whew, we have 24 volts. The lamp is really, really on. Alright, it's taking 1.4 amps actually, and the voltage has been reduced to 6 volts because this lamp is a current hog, and the transformer I think is not really capable of supplying all that amperage it needs. At 18 volts though, it can supply more amperes, and at 13 volts even more. So you can have more power actually. 12 volts is the best, and then we go down to 9 volts, 7.5, 6 volts, 4.5, 3 volts, and then 1.5, back to 24. Alright, so if I put it on, for instance, 9 volts, I can go ahead and disconnect this, or I can turn it into AC, but you see the light is actually turning on with a little bit more brightness because the AC, when you put it into AC, it doesn't have to go through all those rectifying diodes and everything. It just directly makes its way to the lamp through the transformer. But once you make it to DC, it's going to have to go through all those diodes and everything, and each of those diodes produces 0.7 volts. So that's why you see this. And I can change the polarity. Of course, you're not going to see that happening in a lamp because the lamp turns on anyway. And I can go on with the automatic regulator. So I can go on and increase the 0 to 9, or I can just make it 0, right? I can go slightly higher, 12%, 18%, 22, 25%, 30%, right? 40%, 50%, 60%, 70, 80, and 90 are basically almost the same. Alright, so I'm going to actually change the voltage to something more visible, right? Let's say 18 volts. And then I'm going to come back here. You see as I slightly go up, the light of the lamp goes higher. It's not a very smooth transition, I know, because the digital to analog converter I use, the values of the resistor are not properly set. So even at 0%, you see we still have the light on when it shouldn't be. So if I change the voltage down to 13 volts, it's going to be from 0% to 100%, from 0 to 13 volts. So the 100% would be 13 volts, and 0 would be ideally 0. And I'm going to show you the remote control and how that works as well. Can I come through? Alright. So I connected this, and I have the remote control in my hand, right? Actually, the desktop remote control. So I'm going to show you how it's going to work. Once this is connected, this volume is going to be in charge of the 0 to 100%. This display actually is going to be displayed, but it's not going to do anything for you. So once you put it on automatic regulator, you can choose the voltage you like. Alright, so let me just go ahead and connect these wires here. The wires are not connected, right? And I should have the lamp at some, yes. You see this volume, it can give you a very smooth transition because as I turn it, you can see the light going on and off. And then you can see the voltage changing here too. From 1.2 volts, I'm just slightly moving it very, very slowly to 3 volts. It's actually, the resolution is actually 0.1 volts, so I can change it to whichever volts I want. But if I would actually remove the volume socket, you will see that the volume socket that is inside the device will switch back to the DA converter. So if I just plug this out, let me see if I can find this here. See, it's on 5%. Plug this in, it chooses the volume over the DA. Alright, so I'm just going to connect two LEDs to show you that this polarity is actually working as well. Alright, so I connected two LEDs together in the opposite direction. So the anode of one is connected to cathode of the other, and the cathode of the other is connected to anode of the other, all in series with a 1K resistor, which is 250 milliwatts. I think we should do for just two LEDs. And I'm going to connect the LEDs to the power, as I have 18 volts out, because this is the unload voltage. Remember that in this power supply, I actually never use any switching power supply. So there's a no load voltage and there's a low voltage. The no load voltage is definitely higher than the load voltage. That's just how transformers work. For instance, if you have a 12 volts transformer, if you haven't connected anything to it, it will give you as the output something about 15 volts or maybe sometimes 16 volts. But once you connect the load, and say the transformer is rated at 1 amperes, once you connect it to a load that is going to take that at 1 amperes and it's going to use all that 1 amperes, you see that the voltage is going to go down to the 12 volts that the transformer is rated at. Otherwise, you'll see the transformer is providing you with a much higher voltage compared to its rating. So I'm going to connect this, and one of the LEDs should turn on. I don't know which one. Yeah, okay. The red one turns on right now. That means that this is the cathode of the red one, and yeah, you can see the sign actually. This side of the LED, I'm not sure if you can see it on the camera, but this side of the LED is the flat side, so this is the cathode, and the other side is the anode. So I'm going to go ahead and actually change the polarity. You'll see the other LED turning on, the yellow one. Alright. There you go. The yellow LED turns on. That completely means that the polarity has changed. You see the red LED turns on. Now I'm going to go ahead and change it from DC to AC. And then you're going to see both of the LEDs turn on. That is because AC has no polarity. And therefore, both of the LEDs are going to turn on because 25 times in a second, the polarity is going to be in favor of the red LED, and 25 times per second, the polarity is going to be in favor of the blue LED. I'm sorry, the yellow LED. And because it's so fast, 50 hertz is so fast, you won't be able to see them blink, but they're actually blinking, but it's much faster than you can see, at a rate that is much faster than you can see. Alright, so I'm going to go ahead and make it AC. See both of them turn on. Actually, you can see it blinking a little in the camera, but with my eyes I can't honestly tell. But as soon as I turn it to DC, you see that one of them turns on, and it's actually a very smooth light. You don't see it blinking at all. So that's about it. And I'm going to actually talk about the circuitry of the DAC and the voltage and everything else. For now, I would like to demonstrate the safety feature of this power supply, which is really nice. I think you have to see it. I made it basically with a temperature meter and some pieces of wire, and it still works. It just works. So I'm going to go ahead and short circuit this. The circuit is connected. It's in DC. I'm getting 18 volts out. It's in 12 volts. I'm going to go ahead and short circuit. You'll see a crazy amperage flowing through the circuit, and you probably see the voltage drop a lot, maybe down to 2 or 3 volts. But I'm just going to go ahead and do it. And you'll see that the power supply is going to turn itself off. Let's just watch it. Oops. 6 amperes, 7.2. Look at that. The voltage is almost 0. But you see the power supply turn itself on, turn off itself. See? Yes, it's off. That's how I design it. So if I make it a short circuit, a piece of wire inside, I think I put it this side, is going to get warm. A piece of wire is going to get warm, and there's a PTC connected to that. The PTC is connected to a transistor, which detects the changes in resistance and shuts the whole circuit down. And that's just how this power supply works. And it's not going to turn on again until that piece of wire is cooled down. So if I turn it on again, I think it's going to turn off itself. It's going to take about 1 or 2 minutes for the circuit to cool down, and then you can turn it on again. So that's about it with this power supply. I hope you've enjoyed some of these features. Sorry I don't have the remote control, the RF remote control. You saw it in the pictures, but I can't actually show it right now. I just lost it during coming to Malaysia, and I feel kind of sad about that. I keep saying that. That is it. That is a great power supply I did a long time ago. I'm going to make a new version of this, though, that is going to work much better with a microcontroller, perhaps, that is going to have a very stabilized voltage. So we shall continue with the circuitry of this guy. I'm going to explain how all the circuits work. The lower part is just a bunch of meters and transformers. There's no switching power supply inside this. But the upper display has all the controls and all the logic circuits and all the relays that actually control all these lights and everything. You perhaps notice a ticking sound whenever I change the voltage or went from one option to the other, and for instance from AC to DC. That is because there are a lot of relays inside, and some of them are really cheap, so sometimes they don't work. But like I said, I just had anything at hand and I just used whatever I had at hand. One of the relays is 12 volts, one of them is 9 volts, the other one is, I'm talking about the coil voltage. And, I just had to put it all back together with a few resistors and whatever and just, make it work. So it took a long time actually. This project took me a year to finish, but it was worth it and it taught me a lot. I think in electronics you can learn everything once you do projects. I'm going to turn this off.
Alright, so we're going to discuss how to design a digital circuit because I believe that I had to include this part into the video. So you see what is the general procedure of designing a digital circuit, because the way that I design my power supply isn't really standard in an engineering way. I would say it's just a waste of resources in many aspects. And the way I designed it was that I designed different small circuits and then I just connected them all together and I ended up with that big circuit. Well, how are digital circuits designed anyway? They're designed depending on several factors, including based on the number of inputs and outputs, based on the expected behavior of the device, what do you expect your device to do for you, and based on the technical limitations of the device, what are the conditions that this device is going to operate in, and how much power is it supposed to output, and how much power is going to come into its input. The amount of space this logical circuit is going to occupy, perhaps the voltage that this logical circuit is supposed to work with, the speed of the operation of the device, how fast do you wish your device to be, based on whether this device is a standalone circuit or not. Is it going to just work alone, or is it going to be used in a network of digital devices, and is it supposed to communicate with them as well, or no? Is it just going to send information? These are all things that you should consider, and also many other factors that are included in designing a digital circuit. I just actually wrote whatever came to my mind, so let's just pass this slide. Well, you want an example, right? Alright, let's go ahead. We have a boulevard, and in our boulevard we have 3 photocells. At least 2 of them must confirm lack of light, so then the street lights can all turn on. Now, sometimes we do this in the street lights just to avoid turning on the lights altogether for no reason, because there might be a bird sitting on a photocell, one of the photocells might be covered with something for whatever reason, and it would just send a false signal to the switch and turn on all the lights in a boulevard. Now these photocells are installed like this on the lights usually, in a boulevard like this, right? Now in this boulevard I think every light has a photocell on, but we assume that we only have 3 photocells in a boulevard. and these are all inputs, A, B, and C, and the power supply is all considered as Y, as the output. So they're installed at a large distance from each other, assuming that A is installed in the beginning of the boulevard, B in the end of the boulevard, and C in the middle. So moving on, I have 3 inputs, A, B, and C, and 1 output as Q. Alright, so this is my boulevard, right? I have all these lights, but they depend on at least 2 of these sensors confirming lack of light. And for whatever circuit you want to design in electronics that is digital, mostly you should have a truth table. So your truth table is very important because it allows you to reduce the number of logic gates you're supposed to include in a digital circuit, make your circuit actually economical. So I have my 3 inputs, A, B, and C, and my output is Y, right? And I just chose to organize all these numbers based on the binary. You see this is 0 and this is 1, this is 2, this is 3, because I only have 3 inputs, so I would end up with 7 numbers only. There are only 7 possible situations that could happen having 3 photocells as my inputs. So my output is this, and I choose to turn on the output on the specific occasions where 2 of my inputs are 1. So I have 2 of my inputs 1, you see C and B, I have them 1, and my output is 1. I have 2 of my inputs here 1, my output is 1. I have 2 of the inputs here as 1, 1, and well, all 3 are on 1. So great, I'll just choose this one as 1 as well. Alright, let's move on to the next slide. And here, you see the picture gets a little darker, so one of the photocells reads 1, which means lack of light. But it's not enough, I need at least 2 of them, so the lamps are still off. And then, the picture gets even a little darker. 2 of the photocells read 1, and here I have all of my street lights switched on. Because, well, my input B and C are 1, so the output is definitely 1. Alright, here we see the whole picture is almost dark, and I have 3 of the photocells reading 1, and of course the street lights are on. So let's move on to how the truth table works and how it can simplify the logical circuit. Alright, so here's my truth table, right? I know I have 3 inputs, so I will name them A, B, and C, and then my output I will usually name it Y. And then for the inputs, whenever you want to write a binary input, binary number that is a large number that is supposed to be from 1 to 10, 1 to 20, 1 to 30, you don't have to really memorize every number from 1 to 20. All you have to do is to follow this method. You see what I do here is that I first inserted 0 as the least significant bit in my number, and then I insert 1, and then 0, and then 1, and then 0, 1, 0, and 1, right? Because 7 is the last number. I cannot continue till infinity. And then for the B, as the second least significant bit, I will choose 2 zeros, double 1s, double 0s, and then double 1s. And well, for the third one, I think you can guess it right here. I will choose 4 zeros and 4 1s. Now if I had another 4 rows, I would choose 4 zeros again. And right now it actually makes sense. This is the binary 1, this is the binary 2, binary 3, binary 4, binary 5, binary 6, and binary 7. Now I want to choose my outputs. I said whenever both of my inputs are 1. So let's see where it applies. Here I don't have any inputs 1, so this is definitely a 0. Here I have only one of my inputs 1, so this is also 0. Only one input 1. 0 again. Oh, 2 of my inputs are 1. Great. I'll put a 1 in here. Only one input, so this is 0. 2 inputs are 1. Great. 1. 2 inputs 1. That's a 1. And 3 inputs, I couldn't even agree more. This is definitely a 1. So here I would actually like to circle the rows that I need, and I would like to write my inputs in the logical sense, and it would look something like this. What does it all mean? Well, that means that I want a 1 on these particular numbers, 3, 5, 6, and 7. 3, 5, 6, and 7. So if I want to actually write the logical circuit of what I see here, it's not that difficult, but it's very congested. So because I want to lower the number of logical gates that I will finally have, I want to simplify this circuit further. What do? Well, I add it into the Carnot table. It's actually a method to reduce the number of logical gates you want to use in your design. So here, I divided my inputs A and B and C into two sections. A is on one side, as you see, B, C are on the other side. A can only be 0 and 1, right? Only 0 or 1. So I just put one row as 0 and the other row as 1. As for my columns, I have B and C. I put two of the columns as 0 and 0, 0 and 0, 0 and 1. Well, here we have it. 1, 1. Here we have it here. And then 1 and 0. 1 and 0. If you see, the other columns are actually repetition of the other columns. So like the column 1 here for B and C is the repetition of column 5. And the column 0 is a repetition of column 4. So we don't actually write everything into the Carnot table. We just write whatever that is not repeated. And what did I put these ones here? Well, they are actually my output, if you notice. This output is at where A is 1. Okay, so that means here. And where BC is 0, 1. Yep. This is the output 5. A is 1, B is 0, and then C is 1, right? So I can put a 1 in here because my output is 1. I can circle these two ones, these two cells, because they both have a 1 and they're actually attached together and they're even, right? If I have 4 cells, I could add them together. I cannot make a bigger line in here because that would make a number of 3, and that's not what I want to do. So I go ahead and make another circle here because I have 2 cells connected together. It makes an even number, and it's nothing illegal. And then, oh, everything just showed up, sorry. Well, and then I can go ahead and make my last circle. Don't let these distract you, I'll just explain in a minute. Alright, so I can go ahead and make my last circle and write down my logic based on that. Now, how do I actually get to Q equals AC or AB or BC? How do I get to this? Well, you have to take a look at your Carnot table and see whenever you move in this direction, right? What are the variables that change? What are the numbers that change? And what are the numbers that stay the same? So here in A, I'm in the row 1, right? If I move in this direction from left to right or right to left, doesn't really matter, this number 1 is going to stay the same. It's definitely the row of 1, right? So when I move in the row, I have the number 1 as the constant. So A is definitely going to be written because this number is staying constant. If it was changing from 1 to 0, which is not going to happen in a row, it was not going to be a constant, and I couldn't write it here. So I'm writing A. How about C? What do I write C? Well, if you take a look in here, we have BC, right? So this is basically B, the other one is C. This is B, the other one is C. If I move from this cell to the other, you see the B doesn't stay the same. B from 0 goes to 1, but C does. C does stay the same. So C is the stable number in here, and that's why C gets to be written here. So A stayed the same, C stayed the same. I wrote them both together as an AND logic, gate. And then I will OR it with A and B. Why B? Well, because here I have, if you take a look at this circle, I have A staying the same, and also B staying the same, but C doesn't. You see, C changes from 1 to 0. So I cannot write C. I can only write A and B. Or with B and C. If I move from top to bottom, or if I move from bottom to top, you see the A is going to change anyway, so I cannot write A at all. But the two things that do stay the same are B and C. And therefore, I just write both of them. So we write the logics together. We will write A and C as an AND. This is the A and C AND. It's connected, as you see, it's connected to A and also connected to C. This is my A and B AND gate. It's connected to A and B, obviously. And then I have B and C AND gate. This AND gate is connected to B and C, as you see here. And they're all OR together. Well, their output is connected to an OR logic as is seen here, and this Q or this Y is going to behave exactly as is mentioned on the truth table according to its inputs. So whenever the inputs are going to show the number 3, 5, 6, and 7 in binary, it will show a 1. And that's just a short demonstration of how a digital circuit is designed. And then from there, you can choose the ICs that have these logical gates to get in them. And then you can connect the ICs in the appropriate manner, and well, have your logical circuit design. That's as simple as that. And that's about it. So right now you saw how a digital circuit is designed. That's a very small example. That's a very simple example. Here I'm going to actually demonstrate how I designed my circuit and how what was my approach, which might seem funny to you, I understand, but well, at the time I was not aware of how a real digital circuit is designed. I didn't know this way, so I just tried my own way. And my own way was to ask people what to do. So I just jumped in like a madman and tried to make it work. I asked a question on Yahoo Answers because I knew that with the IC 4017, CD4017, I could actually choose between the outputs of my transformer from 1.5 volts to 24 volts because it had 10 outputs, right? But the problem was that it could only count up. So if I wanted to go back from 9 volts to 4.5 volts, I had to go all the way to 24 volts to get to there. So one of the users on Yahoo Answers actually suggested me to use the combination of two ICs, 4029 and 4028, and I tried to use them several times in the design, and as you'll see in the simulations that I've made, these ICs just work great. Alright, so let's just jump into the simulations and see how they function. I wanted to show you the circuit for the inputs and outputs. This one. So as you see, this is the circuitry for a single push button. This is the up button, and for the down, right, and left buttons it's just the same. And I used two transistors, one positive, one negative, to make this work. And these two contacts actually represent the contacts on the body of the device in which you're just going to touch. And well, in the software I can't touch them, so I use a push button to represent a touch. And here, if I run the simulation, you see whenever I press the button, the lamp turns on. This lamp represents the output of this switch, so the logical circuits decide whether to count or move an LED or you name it. So that's a very simple circuit. You see the same thing has happened here, left button, and then the right button, and then the down button. Alright, let's just move to another circuitry simulation. So here's what has happened when I tried to interface the touch input with the other inputs of the device. You see the 4 buttons have been repeated on the desktop remote control and also the RF remote control. Well, these 4 buttons stay the same, the touch structure stays the same, but in order to reduce the noise, so there's not going to be any noise added to the inputs of the touch, I needed to isolate this circuit through a photocell and a diode. And then I could control the diode with anything I wanted. I could control the diode with an RF remote control, with a simple switch. So for now, let's just do a simulation. So if I press the push button, you see the light turns on. Let me zoom in. You see the light turns on. And here I can actually do the same with the photocell. You see? As I increase the lux in here, the photocell is going to reduce its resistance, and therefore turn on this transistor, in which turns on the lamp again. And as I reduce the amount of light, everything is going to shut off. You can assume the same thing happens with this LED. So if I turn on the LED, actually this doesn't work in the simulation, but in reality it would work. I promise you. So when I press this push button, it's going to turn on the LED, and then the LED will turn on the photocell, and then the photocell will turn on the transistor, and then boom, I got my output. So that's about it. Nothing special. Alright, let's move on to the other part. What else do we have in here? Alright, so you see in here we have a normal 555 connected to my 4017. This 555 right here is biased in the monostable mode. So whenever I press this push button, it's going to make its output high for a specific amount of time depending on the capacitor and the resistor's values, and then go off. If you don't know what debouncing is, just Google it, you'll find out. If you don't use this 555 for debouncing, your 4017 is going to count many more times than it should. So here I'm going to run the simulation just to show you how the monostable works. So you see, as soon as I press the push button once, it's going to make its output high just for a short amount of time, you see, and that would result in one count, as you see right here. Alright, so what is this other circuit? Well, I used a lot of 4017s in this power supply. Well, you could basically use a flip-flop with a reset input, but I just chose to use this because I didn't know about flip-flops and all that stuff. I just had a circuit at hand. I had a 4017, I had a 5555, and I basically made the whole power supply by these two ICs and a few more. But 555 was always there, so it was very useful. Output 3, or Q2 here, is connected to the reset button. So as soon as it gets here, it resets itself and goes back to output 0. So what have I created here? I have actually created sort of a flip-flop. So you see, whenever I press the button, it's going to count 1, and it's going to be either 0 or 1. Now this is very helpful. This is the circuit that decides whether the power supply should be on standby mode or it should be turned on. When the power supply is actually on the standby mode, I should note that I didn't turn off all the circuitry and all the logical circuits. When it goes on the standby mode, all that turns off is a few bunch of transformers and also the display. The logical circuits are going to stay on, so that's how I try to get around creating a memory effect. Alright, so I think I'm done with this. This circuit is also used for the AC and DC section, and these lamps represent the output of the 4017. You can assume two different transistors instead of these two lamps, in which are in charge of turning on and off two different relays, in which choose between AC or DC of the output of the power supply. Alright, I'm going to start small and build on the complexity here, so it's not going to be too difficult. Alright, you remember the animation of the power supply when it was in standby mode? It was actually very easy. Again, a 4017 and a 555. So here, if I run the simulation, you see this one is on astable mode and it's going to keep producing this signal. This clock signal is going to drive the 4017, resulting in this animation. This animation is created by connecting the LEDs through two arrays of diodes, one in the right direction and the other 5 in the wrong direction. So you see this going back and forth. Well, nothing important there, I just wanted to explain. So earlier in the video I told you that there's a circuit in the power supply which decides whether it should be on or on the standby mode. That circuit is actually a little bit more complicated. The circuit you see here is responsible for the power supply being on or off. Now how does it work? Well, I use this 555 in the astable mode. So whenever you touch the terminals, these transistors are going to make their output 1. This transistor will stop halting the 555. Therefore, the 555 will start oscillating the 4017. And whenever the output reaches the Q8 or output 9, it will be one pulse or one clock for the 4017. And this 4017 is actually a flip-flop. So whenever it receives a pulse, it is going to change its state from 0 to 1. And whenever it does, the power supply goes on. So the simulation has started. I'm going to press the button. You see, as soon as I press the button, my 555 starts to oscillate. And once it does, my 4017 starts to count. And as soon as I let go from the button, everything is reset. Not only the 4017 is reset, but my 555 is also halted by this transistor. Okay, it just passed the Q9 and you see the state of the second 4017 change from 0 to 1, resulting in turning on the power supply. You can assume that this Q1 is connected to another transistor which is in charge of turning on the display and some other transformers and other things, in which allow the system to operate normally and look as if it is on. I'm going to press the button again. So you see, as soon as I release it, it goes back to 0. Why is this important? Why does it have to always go back to 0? Well, because as I mentioned previously, this power supply operates only by 4 buttons. And these 4 buttons are in charge of everything. Even the power button you see on the power supply is actually the right button. So for choosing options, as this turn on button is actually the right button, I might press the right button several times to get to the desired option, so that I can make a change, right? But that wouldn't affect the power supply to go off. You see, if I just press it and let it go, it's never going to change the state of the power supply from on to standby. Alright, so let's just move on to the next circuit, shall we? Oh, not this one. This is definitely not the circuit. Alright, let's see. What other circuit do I want to talk about? So I talked about the inputs. I talked about the combination of 555 and 4017. I talked about the inputs combined with other inputs and how that works. I talked about how the power supply turns on and how this touch delay works. I also talked about, oh, I haven't talked about these yet. Alright, let's just jump right in. Alright, here we go. So here I just wanted to show how you can actually turn on different segments of a 7-segment and use the 7-segment to show letters to you, even though you're not using any driver. You see here I'm not using any driver IC, I'm just using a bunch of diodes to turn on the specific segments of the 7-segment display in order for it to show me a letter. So if I would run the simulation here, I can press button 1 and it will show DC. Why? Because if you follow the wire, it goes through these diodes, and these wires connect to specific segments of the 7-segment display. And you see, as I turn on the second switch, I get the letter A. If I had turned on this segment, it would show 8. What happens if I turn on both? Of course, they override each other and you just see 8. Alright, so that was a simple circuit, wasn't it? Let's move on. Here you're going to see the same 7 segments operated by 2 transistors in which are connected to another 4017. You're going to see this IC all the time in this power supply. This IC, this 555, is connected in the monostable mode. I think you can tell by the shape and the connections. And as soon as I press the button, it sends one pulse to the 4017, making it change its state and make the Q1 as high, and therefore turning on this transistor, in which is going to show the letters A and C. And if I press it again, it's going to turn off the first transistor and turn on the second transistor, resulting in showing the letters D and C, which means DC, of course, direct current. I'm not sure why I should explain anymore, because it's just very simple. And take my word for it, it is really simple. Let's move on to one of the circuits that is actually a little bit more complicated and quite interesting actually. You remember the percentage shown for the DAC? Well, this is it. This is actually a counter made by the ICs 4029 and 4511. 4511 is a driver for the 7 segments, which has the BCD input, of course, and 4029 is a counter which counts in binary coded decimal, which is the BCD output we have in here. It also has inputs which allows you to override the numbers, but that's another story, we're not going to get into that. So obviously one of the counters is in charge for one 7-segment and the other counter is in charge for the other 7-segment. This one having the lower value and this one having the higher value, obviously. So I had to connect the ICs by this carry out pin, and this carry out pin is actually high most of the times. So once it reaches the number 9, if it's counting up, it will be 0. And carry out being 0 is the clock of the counter. And that will cause another count in the digit which has the higher value. So here I'm going to start, as you see, it goes 5, and it reached 9. You see the carry out is 0. One more count and we have 10. And you see the carry out is high again. So I'm just going to do this again so you see for yourself, but this time I'm not going to stop. 20, and then we have 30, and then we have 40. There we go. And then you can also count down. The counter of the lower value digit, whenever it is going to reach 0, it's also going to make the carry out as low. And that would cause the higher value digits counter to count down. I should also mention that the counting up or counting down pin has been shared by both of them, and it's also networked with the up and down buttons. So here I'm going to count down. We have 30. You can just take a look at that carry out bit. It goes 0 every time I try to do this. And 99, here we have it. Here for the 555, I use the same technique. The 555 is usually on halt, and it only activates whenever I press either of the buttons, up or down. Alright, so let's just get away from this circuit as well. This is still simple. This is still very, very simple. I'm going to show you a large circuit. Well, actually this large circuit is also a repetition of other circuits altogether, but here I use another trick. I just talked about the BCD line in here and how useful it is, and here I'm going to show you exactly why it's so useful. So in my power supply, I needed to show the numbers 1.5, 3, 4.5, 6, 7.5, 9, 12, 13.5, well, I didn't really show the 0.5, 18, and 24. So what do? I can't really make the counter to jump. Well, I use another method. I had the 4511s, I did both drivers, and I thought, well, I could just manipulate the BCD line and show the numbers that I want. And I did exactly that. These diodes are connected to the output of a 4028, which is a decoder. My counter here is a 4029. Well, because I wanted to be able to go back and forth between the outputs of my transformer, I used a 4029. I could have chosen the 4017, but I didn't because I wanted to be able to go back and forth between the outputs of my transformer. So it's the same circuit there for counting up and down using the same 555 with the halting system. So here, alright, zoomed in. Alright, let's go. So as soon as I press the button up, you see the BCD changes here, and then according to the BCD code, the right input turns on. And this input is connected to these diodes, makes these diodes 1, and therefore manipulates the BCD codes of the driver ICs, resulting in showing these numbers. And in the specific occasions, I had to turn on the point. So this is actually 1.5. This is the LED in there. So once I press the up button again, it shows 3. And if you just notice right now, the 7 segment actually turned off. Well, you can't really do that. Your driver IC is always going to show some number, whether 0 or 1 or 2 or 3. It can't just go off. How do I do that? I didn't disconnect the VCC of my IC or the VDD of my IC. How did I do this? Well, it has a blanking input. So if you turn the blanking input 0, all of your 7 segment is also going to turn off. So that's what I did. There's a transistor controlling the blanking input, and it's also connected to some of the diodes here. You see this was the first input, this is the second input, and you see one of the diodes goes specifically to this transistor, in which activates the blanking input, resulting in this 7 segment to go off for this set of numbers. I don't need it to be on. I don't need it to be 0 or 3. I just want it to go off. So I'm going to go ahead and press the up button again. 6, 7.5, 9, 12, 13, 18, and 24. And if I press it again, it goes back to 1.5. And I can just do this backwards. I can go backwards because my IC can count backwards. I'm sorry, my IC can count backwards and onwards. So nothing more to say about this circuit. I think it's just a bunch of diodes manipulating the BCD. But I had to actually make the BCD low prior to connecting any diodes or anything. So the BCD is actually low, connected to low by 100 kilo ohm resistors. And then the right pins are activated by the right diodes by the right outputs, resembling the right output of my transformer. Alright, let's move on to the next schematic, shall we? It's getting interesting, isn't it? So I just showed you how that system worked. It actually activated the right diodes, resulting in the right numbers in the BCD line, which then showed us the right numbers. how do we actually get outputs from this? Well, I don't need these outputs. I don't need the diodes. All I need is the BCD code. I can have another 40 to 8 to control my transistors, in which are going to control my relays here, my array of relays that are controlling the outputs of my gigantic transformer. The numbers are going to be shown according to the right relay being turned on. So I'm going to get a good zoom here. Yeah. If I run the simulation, I don't know why it shows the number 18. And showing this number, it has to be connecting some of my, yes, it's actually showing the number 18, which is 18. And 18 was the 9th output of my transformer. And you see this relay is actually on, but all the other relays are actually off. So let's go ahead and change some numbers, huh? Here I press the up button again, it goes to 24, and you see the 10th output is on. Here I press the up button again, it goes to 1.5. The first output is on. This is what I consider as on, and this is what I consider as off, because if you look closer, this is the 0 output of my transformer, which goes directly to the rectifying diodes, and the NO contact of all of the relays are connected to the same wire, which then goes to my rectifying diodes again. Therefore, if one of these relays is on, I'm going to get that output of my transformer connected, well, you guessed it, to the rectifying diodes. And that's how this whole switching thing works. So right now it is showing 1.5 here, and the first output of my transformer is connected to the network, and that means I have 0 on one side of my rectifying diodes, and I have 1.5 volts connected through all these wires coming down to the rectifying diodes. So here I press the up button once more, and you see the second relay turning on. That means that 1.5 plus 1.5 is actually 3 volts. So my 3 volts output is connected to the common line and then going all the way to the rectifying diode. So I think you get the picture here. But how does that happen? It happens through the transistors that are connected to the 4028, which is reading the same BCD code as the 4028, which is showing the numbers up there. Here I'm going to go one round, and you can see these relays connecting to each other. If you're watching this video in full HD, I think that will help. Here we have 7.5 volts, 9 volts, you see the 9 volts relay, 12 volts, 13 volts, 18 volts, 24 volts, and all the way back to 1.5 volts. And the next circuit you're going to see is about the position of relays and how the relays are connected in this whole power supply. You see we have the AC and DC option, we have the open and closed circuit option, and we have the option for changing the polarity of the power supply's outputs, and we have so many other options in this power supply. I wanted to actually connect all the circuits together and make it complete a schematic for you, but sadly my simulator is not going to be able to run that simulation in that size, so I've tried to actually make a small portion of it, which is still practical, and I hope it delivers the message. So here we go. This is the circuit. You can assume this is the transformer. These are the relays. I just cut them down to 4. This is my rectifying diodes. This is my LM350, that is the regulator I chose, which is able to regulate the voltage from 1.2 volts all the way up to 24 volts. These 2 relays are in charge of whether you want the current to be AC or DC. These 4 relays are in charge of the polarity. This relay right here decides whether your output should be connected to the regulator or directly to the output of the power supply, which has been chosen by these relays. So you could choose the 7.5 volts and still run it through the regulator. You could choose 4.5 volts and still run it through the regulator, because you can literally do that. You could limit the range of your regulator, and the regulator cannot go any higher than 15 volts or so when you choose, for instance, the 18 volts output. Now, when the relevant output is connected, say this one, and these switches are actually the 4028 IC that activate the right transistor depending on the status of the BCD bus. This is the order of AC and DC function, and also the LM350. So here, if I turn this transistor on, if I turn this transistor on, we choose the original current over the regulated current that would come out of this output. If I turn this off, I could choose what voltage would I want through the potentiometer, from 1.2 volts up to 24 volts, depending on the input that I have chosen. So if I have chosen the input of 9 volts, I could only have 1.2 up to maximum 9 volts, which doesn't happen. I would probably have 1.2 volts up to 7 volts or something, or maybe less. There's also another circuit that I didn't really show in here. So anyway, if I choose my original wire that is coming through the rectifying diodes, then here I could choose whether I want the DC version or I want the AC version. Because if I press this button here, you see, the relays will choose the original AC current. You see the AC current is coming through here, it goes through. Here, the AC current is coming through the relays, it passes through, no problem. And if I disconnect this button, it will choose the DC version, whether the DC version is coming through the regulator or whether it's coming through the rectifying diodes directly. And then I could choose the polarity in here. So what happens here is that the DC current comes here, this is the positive DC current coming here, and then it goes through this relay, and then it wants to connect. Alright, so since both of them are off, actually, nothing is connected. So either this switch has to be on, or the other switch has to be on. So if I have these two relays on, the current comes here, well, no connection. So it chooses to go through this way, which makes a connection, and this connection is actually my output. Now you might want to use 2 relays for that, but because my relays have a shared contact, I had to use 4 of them. So then it would be safe, and it would actually make sense. So that's about it. That's how the power circuit works. The actual power circuit has more connections than what you see in here. And these switches that I mentioned, they all come from the logical circuit. But here I just try to simplify everything to be able to explain it to you and to be able to make it comprehensive. So let's see what other circuits are there to explain. And I'd rather be quick because this is taking quite a long time. Alright. So I explained these guys. I explained these guys. I explained them. I explained them. Yeah, I did. So these were a couple of documents that I actually used. I went to this website. It was called something I don't remember right now. These are actually the documents I scanned to maybe use in it later on, but well, there's just some misprints and then more prints, and then A and B, C means what, and then oh, this is the IC that I used for the remote control, PT2262. The encoder ends with numbers 6 and 2, and the decoder ends with the numbers 7 and 2. These documents are quite old, and this is about how to trigger and how to bias the 555 in different modes, and the formula of the on and off times of the output, and etc. etc. And I used a couple of power transistors, I think, I don't know where, to turn on the fans or turn off the fans, because the fans turn on whenever the power supply turns on as well. The fans are not working all the time. And there's a specific fan that turns on for the LM350 whenever it's in action. So those relays are doing something in there. So that's about it. Let's just move through the documents a little bit more quick. Yeah, I actually burned a couple of them because I was experimenting on different lamps and whether the LM350 is capable of outputting at all. And the 555 monostable circuit that was very used all the time. This page I remember was on my desk all the time because it was very useful. I used it a lot for making that flip-flop circuit that I needed. And yes, this circuit also, NPN general purpose transistor, 2PC945. C945 and A733 were 2 transistors I used a lot in this power supply, perhaps 100 times or 200 times. I don't even remember the count. I probably lost the count. And they were basically the transistors I used to interface every component to another component. Nothing is special. Yeah, the regulators and LM350, I think I had a data sheet of LM350 as well. But basically they're biased almost the same way. Alright, LM350, it's a fantastic IC, that's all I can say about it. It has the short circuit protection, so it's really hard to burn this IC. And it has all sorts of protections. It gives you a very clean output, it's very accurate. You can actually drive it in many ways as you wish. If you know how to bias it, you can make it go lower than 1.2V as well. And there's another video about that on YouTube. Yeah, that's all the documents I think I had in here. If you have made it till this point in the video, thank you very much for spending enough time to watch all these documents and bearing my voice that might probably been boring to you. I hope it hasn't been boring to you. If you think I've missed something, please let me know down in the comments, and I will of course appreciate a thumbs up. I will appreciate a thumbs down as well if it's followed by constructive criticism. I'm sure it has stirred a lot of questions in your mind, and please go ahead and ask them, and I will try to actually answer your questions in another separate video and link that video to this one so you could find your answers in that video.